Another really important function that we're going to study is the absolute value function. All right, absolute value function is a little bit strange because you're not really performing an operation like add, subtract, multiply, divide when we calculate these things. Remember, the definition of an absolute value is that it is the distance between a number and zero. Okay, so when you calculate these things, you're always looking for a distance. It's always going to be positive or zero itself. So to determine the graph, we're going to use a table real quick here. And we're going to input some values for x and figure out what the y value would be. And we'll just use a couple here. Let's start at 0. And then from 0 kind of branch out in both directions. So let's go 1 and -1, 2 and -2, and maybe 3 and -3. Right? So we're just kind of expanding out on either side of 0. Well, the absolute value is a distance. It's the output is the distance. And of course, every number has a single distance from 0. And so this has to be a function because there's always one output for every input. So 0, the distance between 0 and 0 is 0. The distance between 1 and 0 is 1. The distance between -1 and 0 is 1. The distance between 2 and 0 is 2. The distance between -2 and 0 is 2. The distance between 3 and 0 is 3. And the distance between -3 and 0 is 3 also. So all of the outputs are positive except for 0. That's not a positive number, but it's also not negative. So definitely none of these are negative on the output side. All right, so when I plot the corresponding points, I'm going to start with 0, 0. That one's at the origin. And that's going to be the lowest point on the graph because this graph never goes down into the negative side. That is not very horizontal, is it? Let's redraw that. Okay, that's a little better. Okay, so start at 0, 0. Then we have 1, 1. So I go over 1, up 1. Maybe I'll go over a few here. Throw one on the bottom. Okay, so over 1, up 1. Then I go -1, positive 1. So back 1, up 1. And then 2, 2. So over 2, up 2. And then -2, 2. And then 3, 3. And then -3, 3. Okay, so those are the 7 points that I just wrote up. If I were to connect those, because obviously I'm just using integers here, but everything will be able to be plugged into an absolute value, right? No matter what the number is, you can always find its absolute value. It's just the distance from 0. And so every point, like 1/2 has a point. 0.1 has a point, right? 0.1 comma 0.1. -2.8 and -2.8. I'm sorry, -2.8 and +2.8. That combination would be on the graph. And so there's an infinite number of points here, and if I extend this out, I'm going to get a line on the right going up to the right, and a line on the left going up to the left. And my graph ends up being a V shape. Okay, comes down from the left, down to the origin, and then back up again. These two lines are on a 45-degree angle. The reason I know that is because on the right here, we actually are looking at the identity function. We talked about that before. The identity function is y equals x, right, where every ordered pair has the same input and output value, right, 1, 1, 2, 2, 3, 3, and so on. On the left side, we have y equals -x. It's also a line, but it has a slope of -1. It's going downward instead of upward, but at the same rate, right? Down 1 for every 1 over instead of up 1 for every 1 over. and they both have a y-intercept at the origin. Okay, so the absolute value could be written as either one of these functions, depending upon the portion of the x-axis that we're talking about. Now, the entire domain for this function is, of course, all real numbers, because, like I said before, you can plug anything into an absolute value and get a distance out. However, the range is not all real numbers, because remember, you cannot have negatives. So it's going to be from 0 to infinity. Okay, so you could almost think of it this way, that the domain is all real numbers, but for each part of the graph, each half, the left side, the right side, you are actually defining the function in two different ways, one on each half of the function, or on each half of the graph. And so you could almost think of it this way, that the absolute value is equal to, well, x, when x is greater than or equal to 0, right? It's for all these positive values of x, the function is x itself, y equals x. It's also, though, negative x when x is less than 0. So for all the x values that are negative over here, right, over here x is less than 0, and over here x is greater than 0. For all the negative or less than 0 x values, we're looking at the negative x function going down. Well, if you think about that, if you had a negative value, if x itself was negative, and then you multiplied it by yet another negative, the double negative makes it positive, and that's how you get a positive output, right? So you have a negative input multiplied by another negative gives you a positive, which makes sense. That's what an absolute value should give you. Okay? Well, these two functions together make up a single function that we call a piecewise defined function, because it's defined in two different pieces or more. You could have more than two. This one is just two. And the pieces are defined over different portions of the domain. Together, these two sets, the interval greater than or equal to 0 and the interval less than 0, together make up the entire domain. Okay? But taken individually, the function looks different over each one. This can be broadened in a more general sense, where you could define a function in a lot of different ways over different regions of the graph. You just have to pick the region and then pick your function for that region. So let me give you some examples of how that might look. So I like the absolute value because it is a nice sort of introduction to this idea of a piecewise function. Something you may be familiar with, and it lends itself well to that. So a piecewise defined function. Okay, so that's what we're going to be talking about for the next few minutes here. Basically, we can look at a function, and we always use a brace to represent a single brace. It's kind of a weird notation, a single brace to represent a piecewise defined function. And then you just list out the pieces. You can have as many as you want. You could have 2, you could have 7, you could have 20, doesn't matter. As long as the functions are defined and they are defined over the parts of the domain that you're looking to put them on. So maybe I want the function x squared, and I keep writing when, but your book might be putting, let me just double check. They put if. Yep. They don't put when, they put if. Doesn't really matter, I'm just trying to be consistent with the book here. So x squared if x is greater than or equal to 0 Actually, let's just go greater than 0. Let's say the function is 2 if x is equal to 0, and let's say f of x is maybe the cube root of x if x is less than 0. Okay, so I've got 3 different parts on this one. I'm making this up as I go. We'll see how this works out. So I've got 3 different parts. And they are separated by 0. 0 is the endpoint for the portions of the domain. So when I were trying to plot this out, for all positive values of x, so that would be everything over here to the right of the y-axis, the function is x squared. What you're going to find when you're working with these, we're going to be looking at primarily our library of functions as our options here, with a few exceptions. There might be a few exceptions where we just have a line and slope intercept form or something that might show up. So here I've got x squared. We know that to be our parabola. Now generally the x squared would start at the origin, go up to the right, go up to the left, and have symmetry. But we only want the portion that's greater than or equal to 0 in the x direction. So we don't actually want this negative side, the side with the negative x values. Okay, we're only looking for x to be greater than 0. Now because we don't want x to be equal to 0 on this, we want that graph to come down but not include the origin. I don't want the origin there because I don't want to actually have 0 on the graph there. So I'm going to leave an open circle at the origin. Now it doesn't really look that way. I'm going to erase some of the stuff in there. So that's what that would look like. Now let's look at the next one. I want the function to be 2 if x is equal to 0. So that means if you were to plug in a 0, the output would be 2. But that's the only point at which the output is 2 on this region because it's the only point in that region of the domain. So at 0, you get the point 2. That just means that the point 0, 2 is on the graph. So 0, 2 is a y-intercept 2 units high. Okay, there's 0, 2. And then for x's that are less than 0, that would be everything on the left here, we want the cube root function. Well, remember, normally the cube root function will go up to the right, kind of leveling off, and down to the left, kind of leveling off, and have this origin symmetry. But because we're only concerned about x values that are less than 0, I really only need the left half, and I can get rid of the right half. Okay, so that left half is what I'm going to plot in here, and it's going to come down and shoot out to the left. Okay. Again, I would keep an open circle there because my function, my domain or region is not equal to 0. It does not include 0. Okay. Okay, so this one had 3 nice portions to it. I have everything plotted. If I wanted to find the domain and range, I could do that as well. Okay, so the domain is found, and you can either look at the graph, or you can just take the union of these 3 intervals or 3 sets: x greater than 0, x equal to 0, x less than 0. Pretty much sounds like everything, right? Positive numbers, negative numbers, and 0. There's nothing left. So the domain would then be all real numbers. Okay, and you can see that from the graph. The right-hand side is all covered by the graph. Left-hand side is all covered. And 0 itself actually does have a point, so that's covered as well. The range, on this one, if you look vertically, this one I can't really get off of the function notation, what I really need to do is look at the graph on this one. What I notice is that the lower part here, under the x-axis, that's all included. So negative infinity to 0 is in there. 0, however, is not included on the graph. So a y value of 0 never has a point. There's no x-intercept. So I put a parenthesis on the 0. From there, going upward, everything gets hit up to infinity. The 2 actually gets hit twice. It gets hit once on the parabola and once on this point. But that doesn't matter. If it gets hit twice, that's okay. As long as it gets hit, it's in the domain, or it's in the range. So the range goes from 0 to infinity on this other side. But remember, it does not include the 0. So I have to exclude the 0 by using a parenthesis on both of the intervals. Okay, so there's a domain, there's our range. If I wanted to find any y-intercepts, I would use, again, that x value of 0, plug it in, I get a 2 as an output. Now what's neat about this is that I can actually evaluate function values based upon this function notation. I could also do it based upon the graph. If I wanted to, I'm going to give you just a couple things like, I don't know, find f of negative 8, find f of positive 3, and maybe find f of negative 1. So there's 3 different values to find. Well, if to find negative 8, well, negative 8, remember, is your x value. It's your input. If it's the x value, then I have to look on my x values here and find which interval the negative 8 falls in. Well, negative 8 is less than 0, right? Negative 8 is less than 0. So it falls into this bottom category, which means this function is the one I plug the negative 8 in. I don't plug the negative 8 into the other functions. It's only that bottom one. And so f of negative 8 is going to be, well, the cube root of negative 8, which is negative 2. Okay? So coming out here to the left, when you get out to negative 8, the function would be down 2 units. Let's get rid of the domain and range for a moment. So I have some space here. If I wanted to find f of 3, well, f of 3, again, 3 is the input, the x value. So I need to put that in and find where it goes. 3 is a positive number. It's greater than 0. 3 is greater than 0. So it's going to go in this top region. So I apply the 3 to this x, and I look at x squared, which is 3 squared, or 9. Okay? I don't need to put that 3 into the bottom equation or into the middle one because it doesn't apply. The x value doesn't apply. It only applies to that top one. So 9 would be that value. So that means that if you went over 3, the graph would be up 9 units. And then finally, f of negative 1. Well, again, negative 1, that's your input. That's the x value. So you look on the different regions here, different intervals, and negative 1 fits into the negative side, less than 0. And so I plug it in here. The cube root of negative 1 is equal to negative 1. That's the only one I would need to evaluate. And again, if you went back 1, down 1, you get a point on the graph. Okay. So that's how we would evaluate these functions. Some of these functions will have 3 intervals rather than, like a point here. Some of them may not go off to infinity. You might have an interval that is finite on both ends. Okay, so like a closed interval or something like that. So there's lots of variety in how these intervals could be constructed. 0 may not be an endpoint. That's okay. But hopefully this gives you an idea of how you can sort of piece together these functions And again, we're going to be utilizing the library of functions primarily as the different portions there.